half of tonight's class. So now we have all the forces for each of the mass. So
Okay.
now let's show the free body diagram. Yeah, FBD is the best friend for civil engineers. The equilibrium. Each mass. The first one, we have a spring force go to the left, spring force go to the right. These two spring forces are different. And we have a inertial force. And don't forget the inertial force, because that's the major difference between static and the dynamic analysis. And we have the external force. And that's P1. That's P1. So who would like to formulate the equation of equilibrium based on this free body diagram? So we have all the forces here. And what would be the equation of equilibrium? This free body diagram. Elizabeth, would you like to try?
Not yet. I'm working on it. Oh, okay. So we have, it's all going to equal P1. And so it's MU double dot plus KU1 minus K2 U2 minus U1 equals P1? That was a guess.
So,
Was that close?
so following the inertial force, so you have plus
Right. The
K1, U1.
P1, U1, and
Minus.
minus, okay, K2.
K2 U2 minus U1. Ooh, that's what I
Minus
said.
mu1.
Okay, equal to P1.
That's actually what I said. Oh,
Yeah, very good.
I got that one right. People, I got it right.
Good job. The same,
No applause from.
similarly, we should be able to do the
I don't even know if they're awake.
second one. Second one, we have the brain force here. Brain force here. And we have the inertial force. And then we have the external load. Okay, now would you like to do this one?
Oh, he just called me.
To equal to Newton.
Did you ask someone to do that already?
Yes, Kayla is working on that.
Wait.
Okay.
So probably I would have you to something work on the third one, if you like, after Kayla's done.
Kayla would love your help.
You can do whatever you want.
All right.
K2 times U2 minus U1. K3 times U3 minus U2.
Okay, very good. Good job. Good job.
I'm so proud of you.
Okay, very good job. So now we have the M3. We have the So Anthony, would you like to do the third one?
Yeah, sure. M3 U dot 3 plus K3 times U3 minus U2 equals P3.
Very good job. So that's all the three equations. So that's why for most MDOF system, which use equations, motion equations, of motion, because if we have three masses, we will have three equations. So now we combine the three equations together because we need to solve them simultaneously. So, equations, motion, or so we combine them together.
We could have.
And the way we organize them, as you said. For example, we combine the terms with U1 and with U2 with U3. And we also break the terms where we have U1, U2, U3, and in appearances. So that rearrange them a little bit. Just simple math here. So far so good. Huh? Any questions regarding the new format here? We break the appearances and combine the factors for U1, U2, U3. We can write. So the reason why we rewrite or reformat the three equations because we want to express the three equations in terms of matrix. So now we write it in matrix. Linear algebra.
Should have taken that.
This is like.
Do you have any taken linear algebra?
Yeah, you're my advisor. I haven't taken linear algebra.
It's a requirement.
Well, shit, I better get on that.
Oh.
I took differential equations.
Linear algebra is not required for this.
No, because we took calc.
I took applied math.
Applied
Had about a week of matrix.
Oh, I thought that both linear algebra and differential equations are requirements, no?
There's a class called applied math for civil engineers,
Yeah, that's.
Yeah,
Yeah, I didn't take
which
that.
has like, I think it covers all those
It
topics.
covers,
in the
like,
class.
yeah, linear algebra and differential equations.
Well, it's not extremely in depth. It's just like basically how matrices work.
I overshot the math. I have a math minor now.
Yeah.
Yeah.
Good for you.
So now, anyway, now we
I wonder if they-
rewrite everything in matrix. we have the acceleration vector here, and we have the displacement vector here. We just need to fill the blanks here.
Yeah,
Indeterminate structures.
it's a lot like indeterminate structures, which we're doing right now.
Yeah, so without the taking linear algebra, how would you do that? How would you survive that?
I listen to Professor Fioclu and hope for the best. This is why I'm always confused in that class.
You did a great student.
I mean, that depends who you ask.
So, the Sultan, would you like to help us fill the first box here regarding the accelerations?
Oh.
So personally, how many elements, how many numbers will be in that box?
We'll have 9, I think.
Yeah, 9 in total, right?
M1 is the first one, right?
M1, so where should we put the,
Northwest corner. Yeah.
okay, okay. That means just,
He's like, oh, it's like he's taken linear algebra.
Like 9 years.
so we have the grades for you, so where is M1?
The first cell.
What's here, zero? We are, okay, so how about the other two elements put on the first row?
3 zeros, right?
Okay, yeah, there you go, very good. And how about the second row?
0,
Be M2.
M2.
M2?
Yeah.
Okay, M2. Oops. M3, huh?
This is Professor Fioclu. That's what this is.
Okay. Very good. So that's the matrix for the next. The max matrix. Similarly, we should be able to do the stiffness matrix here. So online students, any one of you is interested in helping us to figure out the numbers for the elements for the stiffness matrix here?
Yeah, I think I got the first one.
Okay. Please, thank you.
It would be parentheses K1 plus K2 in the top left,
Okay,
and then minus K2.
minus K2. How about zero?
And then 0.
Zero. Thank you, Vishal. Hunter, would you like to do the second row?
Sure, so
K2.
I can do the second one.
that's fine.
Hisham, you want to do the second one?
So yeah, so K2
Sorry.
plus K3,
K2 plus K2, where to put?
the first cell. No, I mean in the middle one, the middle cell,
Okay, middle cell. Okay,
and then plus. No, I'm sorry, in the middle cell, negative K2. Hold on.
what happened here? Oh. Okay, so is it back?
Yeah.
Okay. Oh. So we have
Okay, so I see.
minus.
Okay, so I'm sorry. So Okay, so in the middle cell, just negative K2.
In the middle is
No, yeah, you're right. Yes, yes. Negative K2 and K2 plus K3, and then 0.
Okay. How about the third one?
0.
The third cell in the second row,
K3.
K3?
Negative K3.
Minus K3 and minus K3.
Yes.
Because if you look at the second equation, the factor for the U3 is minus K3. Thank you, Hisham.
This makes sense.
So Hunter, would you like to do the third one for the delay?
Say
Okay, 0.
minus K3
Mhm.
plus K3.
Plus K3. Okay, very good job. Very good job. So that's the
Makes sense, though.
so that's the equations of motion and in the form of matrix. In the form of matrix. So in case where we have only 3 degrees of freedom, imagine if you have a 100-story
Good, thanks.
building, right? What might happen? So, and then you would like to skyscrapers.
I love skyscrapers.
So yeah, so the
That's a bigger matrix.
yeah, bigger matrix. Very good.
Wait, Professor, Yang,
Yes.
if you really were doing a skyscraper, you wouldn't do it like this, would you?
The computer would do it.
Computer.
Computer, that's what I thought.
Yeah.
Like you're not doing a billion by billion matrix.
So now we just combine, and so this is called the mass matrix, right? This is a mass matrix, and this is a stiffness matrix. So, and the other form, we can just use the mass matrix as the acceleration. Plus the stiffness, and the displacement is equal to the force vector. So very similar to the single degree of freedom system. The only difference is that instead of using some scanner variables, we use matrix and vectors. So any questions up to now? As you can see here, because if we can show the free body diagrams, we should be able to formulate the equations of motion for any MDOF systems. So this is for the shear buildings, shear buildings. So now let's look at another case where we have the dynamic foundation issue. Example. Another system here. So for example, in the you have a rotating motion.
Oh, wait, it's a washer machine.
Anyway, it's washer machine or any machine that will exert a moment, the force. Rotating motion. The rotating motion is placed on a foundation where the foundation is supported soil on the soil. So this type of structure can be simplified or can be modeled. So we can model this system by using a rigid beam with two springs on two ends. And the spring constant is different for the two springs. And then when the rotation motion runs, there will be an external bending, external moment as well as the external force and exerted on that rigid beam. And then if we assume there is a concentrated mass for the foundation, this is the concentrated mass. So the mass and the eccentricity to where the machine is. This equal to E. And then if we have the location of the radius L3, L4. So this is the case where we have only one mass, but we have two. We need to consider 2 degrees of freedom here, because we need to consider the vertical movement of the foundation as well as the rotation of the mass, rotation of the foundation here. So in this case, we need to create a coordinate system. So this is where the case we need to consider moment, dynamic moment. This is the inertial location of the mass. This is a concentrated mass. It's equal to M. And after So if the two springs has some elongation there will be a rotation as well as the displacement for that mass. Now this makes sense because remember that the foundation is rigid. This is a rigid. Because the stiffness of the foundation is much higher compared to the much higher than that of the soils. So that we typically assume the foundation is rigid, where the soils can be modeled as two springs. Actually, this is it's more like a dynamics of geotechnic problem. So in some schools, there is a course called soil dynamics, earthquake engineering. So geotechnical engineering has its own dynamic analysis part. Sometimes structural engineers also need to do some dynamic analysis on foundations. So this is one of the case where you have the dynamic foundation issues. So firstly, we need to construct a coordinate system. So for example, we need to consider the rotation of the mass is theta. And then we have the displacement. So the displacement for the first three is equal to U1, and the displacement of the machine is equal to UA. UA. Is equal to UA. Okay. And then it's equal to U. And so the displacement of the concentric mass or the centroid of the mass is equal to UCM. So based on those geometry, we should be able to get the relationship between those factors. So UCM will be equal to UA plus eccentricity and theta. Remember the eccentricity of the mass is equal to E. Equal to E. So we have the U1 equal to UA minus L3 and theta and U2 equal to UA plus L4 times theta. So in this case, we only need to consider, as you can see here, because the foundation is rigid, we need to consider the displacement of the foundation at where the machine is and the rotation of the foundation here. So the other displacement, they are related to the two discrete degrees of freedoms here. So now let's say what would be the freedom Figure diagram. We just show all the forces acting there. So we have the bending moment as well as the concentrated force where the machine. So we should have the reinforced K1 and the K2 and the U2. And where the mass is, we have the and the moment of inertia. The angular acceleration. So in this case, if there is any rotation, you also need to consider the angular inertial, and that's the inertial moment, So now we should be able to formulate the equations of motions or equations of dynamic equilibrium here. So there will be two equations. So if we consider the forces, so how would the first equation be like in this case? So who would like to do the first equation regarding forces?
CM.
Okay, very good.
Plus K2U2.
Okay, good.
Equals P.
Okay, very good. Good job. That's some dynamic equilibrium in the y-axis, vertical direction. We also need to consider the equilibrium of moments. So who would like to do the second equation? Would be
Okay, would be I theta
I zero theta
equal mt.
equal to mt.
Yes.
Thank you, Hisham. My question for you is, so here we are taking the moment about the point where the motion is. For example, the motion is O. We call it point O. So we take we consider the moments at point O over there. So at point O we have a moment mt, and we have a moment I sub 0 times dot theta here. Are there any moment, any other moments?
Okay. So yeah. So mu dot
Times the moment arm times the moment. So in this case, we need consider more here. So we need
plus mu dot times
times what is the moment arm here? That's
L1 or
Oh.
yeah, that's the eccentricity here, right?
yeah, E, right.
That's the E. We use the E. Very good. You got that. You got that. So that's the first moment, and also we have the
K2 U2
times
L2.
and L4, huh? L4. Remember the distance information here. So this is R3 is L4. This is eccentricity. Yeah. So we also need to consider the moment arms. And we have T1, U1, that's minus times L3. U.
Empty. Empty.
And you go to M empty. Huh? So please keep in mind that the other forces also exert moment. So now we have only two equations, but have so many unknown variables. But some unknown, some variables are associated with each other. So we just use the relations between the displacement and the rotation here to rewrite the equations. So that we will have because U1 is equal to UA minus theta plus 2 innovation U4 and theta. So equation. And so we does this make sense? And then the UM is also UCM is also related to the UA. So we can just go ahead and replace this too. Replace this too. We just rewrite it as an M There is no. So that's the three questions with only on the variables UA and theta. And we can also write rearrange this and write a equation. In matrix. Yeah. And that is a dynamic equations of motion of the rigid foundation. So in the two cases, we have already formulated the equations of motion for a shear building as well as for a rigid foundation with rotating motion. If we look at the mass matrix and the stiffness matrix, so both matrix have some very important features. As you can see here, so are those two matrices symmetric? Matrices over here. So the mass matrix actually is symmetric about the diagonal direction. The two elements for the mass matrix on the top right and the bottom left, they should be equal. They should be equal to each other. Similarly, for the stiffness matrix, the top right and the bottom left elements, they should be equal to each other. So that's the most important feature for stiffness and mass matrices. Similarly, if you look at back to the case with the three displacement. This is a mass matrix. So it's symmetric about the diagonal direction. Similarly for the stiffness matrix. So anywhere, actually the stiffness matrix is the same stiffness matrix you use for static analysis. If some of you are taking the indeterminate structure, so that's the same stiffness matrix for, yeah. Okay, so now let's go over an example to see how we can formulate the equation. So that example is based on your textbook, the homework. If you have your homework problem 9.1. So we need to formulate the equation of motion for a system where you have the
A uniform rigid bar of total mass M is supported by two springs, K1, K2, at the ends and subjected to dynamic forces as shown in the picture. The bar is constrained so it can move only vertically in the plane of the paper. Note, this is the system of example 9.2. Formulate the equations of motion with respect to two DOFs defined at the left end of the bar.
and that's 9.2.
That's what I have. Oh, 9.2? Wait. A uniform simply supported beam of length L and flexural rigidity EI and mass M per unit length has been idealized as the lumped mass system shown in a picture. The applied forces are also shown. Identify the DOFs to represent the elastic properties and determine the stiffness matrix. Neglect the axial deformations of the beam. I hope you all appreciated that.
Thank you, Elizabeth.
You're welcome.
So based on Elizabeth's description, I will just show the program figure. So we have a rigid beam supported by two springs on its ends with screening constant K1 and K2. So there is a force and a moment with the middle span equal to P, T, and N. Anyway, you just call it PT and the P theta. So one is concentrated force, the other one is a moment. So, and we are required, since it's a rigid bar, any rigid bar in 2D space has only 2 degrees of freedom. So we only need to consider 2 degrees of freedom, either by the rotation and the translation on the left side or the right end or in the middle. So this problem requires us to formulate the equations of motion based on the translation and the rotation on the left end.
You're using the wrong diagram. You're supposed to use figure P 9.2, which is next to the one you drew.
Wow.
I mean, you do you, but there's like EI and ML to the third, and it's a simply supported beam.
Oh, okay. Well, let's just formulate the equations of motion based on this.
We could do that.
Okay. So if the mass is equal to m and then concentrated in the middle, the uniform bar. So what's the first step? Free-body diagram. We need to show the free-body diagram. Bar. So for example, the bar has been moved from its original direction to the arbitrary location. spring location, where we have the aim displacement on the left is equal to U1, and the rotation of the bar is equal to U2. Sometimes the textbook requires us to use U instead of beta here. The principle would be the same. So, triple diagram. So we will have the string force. So the string force at the left end is equal to K1 times U1 to G1. That's easy. That's easy. So how about the spring force at the right end? What is the displacement for the second spring over here? So should be equal to K2 times the elongation of that spring. What is the elongation of that spring? So the total elongation here should be the total elongation here will be equal to U1 plus L times U2. Right? The total length here is equal to L. And since U2 is very small, actually the actual length should be U1 plus L times tangent U2. But since U2 is very small in this case, tangent U2 equal to U2. You agree with me? Algebra? Oh, calculus, a little bit. Calculus over here. So that the force here is equal to A2 1 plus L U2. And then we also have the external force. So PT and the P theta is theta. That's our external forces and the spring forces. How about the inertial forces? So the inertial forces in this case, the distributed force, So the inertial force this is the inertial force, and so because the unit mass of the bar of the beam is equal to m over L. So the total mass over the length. Then we have the acceleration here and the acceleration here. Does this make sense? You have- Because the displacement along this bar is linearly increasing from the left end to the right end. So the accelerations is different for different locations. So that's why the inertial force should be a uniformly distributed force other than a concentrated. So as you can see here, if you select different degrees of freedom to describe the motion of the rigid, then the problem will be a little bit different. So as you can see here before, we use the rotation and the position and the centroid of the mass. So that would be the easiest ones to solve. And then if we select the displacement for one end of the beam, the solution would be a little bit more challenging here. So anyway, we have the free body diagram. So based on the free body diagram, we should be able to use the dynamic equation to formulate equations of motion. Right? So we will have two equations. The first equation for vertical forces, second equation for moments. So for the vertical forces, the task would be very straightforward. But for the moments, that work here. So that's so any questions so far for the free body diagram? Okay, so now let's formulate the equations. So the first equation is about force, the vertical force. So we just all the forces adding together. We have the force, the K1 and U1 plus K2 and U1. The total concentrated force. So that's that's the first equation. Does this make sense? So the total inertial force should be equal to the area of the uniformly distributed shape of the shape of the uniformly distributed inertial force. That's the first equation. And then for the second one, we just take the moment, but the centroid, but the central, where we need about the centroid. We have the, or we can just we take the moment, the center in the center. Then we have the K1 times U1 times area over 2. And minus K2 over 2. So we have the should be minus. And what is the direction of theta? Theta. So that's about moment. About moment. So does this make sense? So we go back to the free-body diagram. So we take the moment about the center, So we have the moment T1 times U1 times L over 2 as the positive, And we take the counterclockwise as positive. This one minus this force times the moment arm, and then plus the moment induced by this uniform distributed. For this uniform distributed, we only need to consider the triangle on top, because the bottom rectangle at the centroid at the center. So we only need to consider the top. We calculate the area of the top triangle over here times the moment arm. So this is the negative, because it's the counter, it's a clockwise. Plus theta equal to 0, plus theta equal to 0. That's how we got this equation. Any questions? So as long as you have the three-point diagram, the remaining is the same as the structure analysis. I would say the only difference is you need to figure out how to express the inertial forces. And now we just go ahead and rewrite this in terms of we combine the U1, U2 together. We have the N U1 plus ER2 and then we just go ahead and write down the second equation. And now we just write down this in terms in the matrix form. This is an equation of motion. Equation of motion. Of the matrix. So as you can see here, the mass matrix still symmetric. On the direction. Similarly, the simple method should be symmetric. In future, if you got a mass or stiffness matrix that are not asymmetric, that means something wrong with your Venn diagrams or the formulation of the equations. And this is very important for a MDOF system. We need to know what is the mass matrix and what is the stiffness matrix, because we know for the SDOF system, the mass and the M and the K determines the natural frequency, correct? Similarly, for the MDOF system, the mass matrix and the stiffness matrix determine the natural frequency of that system. Since we have matrix here, so the solution for this equation will be multiple solutions, multiple solutions here. So that we will have multiple natural frequency for MDOF system. So next time we will talk about how to calculate the natural frequency. Here we use plural because multiple frequencies here. So I think that's all tonight. Probably I'm going to assign you 2 or 3 problems to practice for this topic, because the formulation of equations of motion for MDOF system is very important. Let me know if you have any questions. Okay, no any questions? Let's stop the class.